All right, and we are back. This is Wednesday, July 22nd, the first part of chapter 24. We are moving along. We're grading test 2. We'll get that the scores entered in Learning Suite as soon as we can. Quiz 6 is due tonight. Should be able to finish that. It's topics from chapter 23 that we already finished, the alkylation stuff. And then let's see, July 24th, this Friday, Pioneer Day, no class. You're off the hook there. Catch up on your studying, do what you need to do some celebration, do something fun that weekend, not just all OChem. And then let's see, homework 9 will be due on Monday. That's when we'll finish up chapter 24, but we'll be starting 25. And amazingly, when we get done with 25, that's when we do test 3. So yeah, we're definitely moving along. Test 3 is what, chapters 23 through 25. So we've got the carbonyl alkylations, the aldol now reaction in 24, and then amines in 25. Very good. Well, let's see. We've got rotating up here on the overhead screen, we have CHEM352. I've directed you to CHEM352 a couple times. We've shown you a few things there. And what we have here is the aldol reaction. And this is where we're going to have an enolate. You can see the enolate right there. Let me turn the spin off. The enolate of one carbonyl here condensing with an aldehyde. It's acetaldehyde here. And you can see as the enolate nucleophile approaches, the purple ball is lithium, so that acts as a Lewis acid coordinating the carbonyl of the aldehyde. And then when they get in close enough proximity, a new carbon-carbon bond's formed right there. So this is the aldol product. So there's a number of these reactions, animations that you can look through. There in Chem3D, it's under the organic button right there. I think it's nucleophilic additions to CO. Oh, there's the Grignards and a bunch of others you can look at there. Enols, enolates, there's a whole separate section there with some aldol animations you can look at. So yeah, look through those and that can help you to review. You can look at those on any device, of course, they're free. Let's look at what we need to know in chapter 24 here. So we're still with enolates and enols here. Those are the nucleophilic parts of the carbonyls. But now we're leaving out the alkyl halides. We're not doing SN2 chemistry. We're allowing the carbonyl compounds to condense with themselves. So the enol or enolate here can condense with another molecule of aldehyde to make this bond right here to give the beta hydroxy aldehyde. Now that's a condensed name into the term aldol, okay? Alcohol aldehyde, aldol. Not Bob Dole, the politician's brother, Aldol, although I think he did have a brother named Al. But Aldol did not invent the aldol reaction, okay? It's a contraction of alcohol aldehyde. And there it is right there. So no alkyl halide, whatever. At lower temperature, 5 degrees, we get the aldol product here. If we heat it up, we get what's called the aldol condensation product, and that's what? Loss of water to give an unsaturated aldehyde or unsaturated ketone, as we'll see. So we actually have 2 reactions there in the aldol. Now we can mix this up, have crossed aldols, 2 different aldehydes or ketones or aldehydes. We'll have to identify which one's which. One functions as the electrophile, one functions as the nucleophile. We have to look at the structure and say which one's going to be which. Directed aldols, we can preform the enolate with LDA and then add in the subsequent carbonyl to give a directed aldol. We can also do intramolecular aldol reactions right here. They look kind of funny, but these products are very useful, forming rings. 5- and 6-membered rings are favorable and very common here. This dialdehyde right here, condensing at higher temperature, that's the aldol condensation intramolecular product, forming a cyclopentene, you see. Okay, not to be outdone, esters are also involved here in the enolate condensation chemistry. This is the so-called Claisen condensation. Again, this one is named after a person. There was a person named Claisen. Aldol, no. Claisen here is an ester in the presence of an alkoxy base, enolate, and then condensed with an electrophilic neutral ester can give us the Claisen product here. Okay. And initially, during the reaction conditions, it's this beta keto ester enolate that's actually the driving force for reaction. You need to acidify things to get the neutral product. So here's the product here. It's formed as an intermediate, but it's actually deprotonated to help drive the reaction forward. So there's a little bit of a tricky mechanistic issue there with the Claisen condensation, but we'll look at that. And of course, there are intramolecular versions of the Claisen. Another person here, Dieckmann, Walter Dieckmann, was a German chemist who discovered the intramolecular Claisen reaction to give these cyclic beta keto products now. Now in America, not to be left out, this was Michael, a chemist at Tufts University, right next door to Harvard. He noticed that these stabilized enolates of beta carbonyl esters and aldehydes, ketones, whatever, these type of enolates can undergo 1,4 or conjugate additions. So this is similar to the cuprate reactions that we saw adding the enones. Actually, the Michael reaction predates the cuprate development, but this can give a different type of a product here. Dicarbonyl, but separated by quite a bit here. And then, not to be left out, we need to go back to Europe, Great Britain. This is Sir Robert Robinson, who developed an annulation reaction, an annulus. There's a term for you, Latin term. What's annulus mean? Yes, a ring formation. So we can form another ring here using a combination of the Michael reaction, conjugate addition, and then an intramolecular aldol. Now, looking at that product, that's tricky to figure out that mechanism, isn't it? In fact, this is the most complex mechanism we're going to see in the entire term. And I like to point out that students that are in the A range usually have no problem handling this Robinson mechanism here. So if you want to gauge your understanding and progress in your class, see how comfortable you're going to be with this Robinson annulation. Yeah, you're going to have to practice it and follow along closely here in class, but that's a good way to gauge your understanding and progress. Yeah, so we'll point that out. So we got a lot of name reactions, right? We got Aldol, Claisen, Dieckmann, Michael, and Robinson. Now, don't worry about those names. This isn't a history class or anything. The names are useful, though. They keep track of these mechanistic pathways and these very useful products. These are very useful reactions that we're going to see over and over again. Now, the carbonyl decision chart here. This is a unifying chart for the previous chapters and then going into this next section, chapters 23, 24. So we've seen a number of these reactions now with carbonyl compounds, acyl compounds, right? We've seen ketones, aldehydes, we've seen esters, amides, all sorts of other derivatives here. And here they are, all are kind of listed with X here, okay? X is a potential leaving group, but it doesn't have to be. If that's a hydrogen or a carbon, right, that's a ketone or aldehyde. And those are going to be different here. So I identify a reactivity, the partial positive position here. That's the first thing to identify. And then make the decision, is X a good leaving group or not? Well, it's a good leaving group if the conjugate acid here is low, pKa-wise, right? That means X, as a heteroatom, as an oxygen, a halide, whatever, can come off as a stable anion, okay? So that means you're going to follow this pathway here that we've been covering. Nucleophilic addition, tetrahedral intermediate, and here's our good leaving groups. We've looked at a lot of different nucleophiles, right? And that leads to acyl substitution. But if X is a poor leaving group, right? If we've got groups here where the conjugate acid is very high, that means that's not going to come off the tetrahedral intermediate. So does it mean it can react? Well, even if it's a bad leaving group, if you answer, no, this is not a good leaving group, then what? You can treat with base, and if it's got an alpha hydrogen, you can deprotonate at that position and form a reactive enolate, okay? So that's the rest of the story. So hopefully this unifies what we're talking about here. The enolate then can react with alkyl halides like we've been doing in 23, or halogens also in 23, but now aldehydes with themselves, right? Here's the aldol reaction. Okay, you can also add an acid chloride or a ketone under certain conditions, or MCPBA, metachloroperbenzoic acid, and you can get an oxygen at the alpha position. That's electrophilic oxygen, right? So these will alkylate or react with electrophiles at the alpha position. Why? Because X is a poor leaving group, okay? So hopefully this unifies and helps you think about, it'll help you review for the final too. So use that chart there as you'd like. Here's the rest of the story that we've been doing in chapter 23, the acetoacetate and the malonate story, right in between the methylene here, low pKa. We can easily form that enolate here irreversibly, right? So it's completely deprotonates there. Then we can alkylate and do other things there, decarboxylate, you know, if it came from malate or acetoacetate, got the carboxylic acid hydrolyzed there and decarboxylate. And then this goes back to the previous chapter, right? 22, where we've talked about the Grignard additions where X is hydrogen or alkyl, and there the tetrahedral intermediate can't break down, okay? And if it's an ester or an acid here, then we can add twice, right? So that's a good review of that. All right, speaking of reviews, let's go over here to the board, and I've got some problems drawn up there. Synthesis problems. Well, these two are synthesis. Come up with a route to go from here, the para-methyl phenol, to that ketone over there. That's actually has a name. It's called raspberry ketone. Comes out of raspberries, has some health beneficial activity to it. And then here's methyl malonate going to this barbiturate drug. And so how would you make that drug from malonate? And then this is a mechanism problem, this chloroepoxide with the acetoacetate under base conditions, and then acidify going to that product there. If you want to pause and work on that, great. Okay, and we're back. So how do we do this? These synthesis problems, think in the reverse direction and which bonds are strategic. So we need to put on the elements of what? Acetone. And if we do that, we can think about an acetone enolate, right? So if we have this enolate, then we can easily form that from acetone and LDA, right? And then condense it with some leaving group here. And where do we need the leaving group? We need it right there, okay? And so if we can form the benzylic bromide, we can turn that into a good leaving group. But we have a proton source here. We don't want to have this active when we do these reactions that are under basic conditions, where we just deprotonate there. So what we need to do first is treat with TBS chloride, terbutyl dimethyl silyl chloride, if you remember the protecting group. That would be the first step. Second step, we'd want to treat with NBS, which is N-bromosuccinimide and light, okay? Or we could have treated with just bromine and peroxide to get that started. So here'd be our intermediate. We'd have the TBS group, that silicon protecting group on there, and now we have the bromide, okay? And now we add in the enolate of acetone that we get from acetone and what, LDA? That would be the best way to go. That's what, irreversible deprotonation. And then if you want to review the mechanism, there you are. And then how do we take off the TBS group? So we'd have to add in TBAF. And that's the tetrabutyl ammonium fluoride that will take off the TBS group. Anyway, that's how raspberry ketone is made. It's made on large scale, and a number of companies are interested in commercializing that as a health beneficial essential oil type compound. Okay, how do we make the barbiturate here from the malonate? Well, we need to react with sodium methoxide. And which one do you want to put on first? Here's our strategic bonds, right? So let's put on the isobutyl first. And then a second step, we'd have to have sodium methoxide and what? The straight chain propyl bromide or chloride, whatever. That would give us this. Maybe I can just draw on the intermediate. Okay, so yeah, that would be our intermediate right here now. Okay. And then what do we need to do? We need to make the barbiturate. And that's made simply by taking urea. You can review what that structure is and heating it up. And that will do an acyl transfer from the ester to the amide-like structure. Okay. Yeah, so not too bad. This mechanism looks a little wild, doesn't it? How do we get to that? But you can kind of map on to the starting material and see where things are going to form. There's our acetoacetate. It's hydrolyzed as the acid there. We're not heating it up, so it's not decarboxylating. So different types of products we can get here, right? But mechanistically, what's going to happen here with the base? Yep, we're going to form that anion. And now we've got two spots that are electrophilic. Well, actually three. Two spots here for the epoxide, right? And the chloride. Which one do you think is going to go first? And this is a primary chloride, right? And so, yeah, I think we want to do that first. Actually, you can do it either way. But the problem is here, it looks like we attack there on the epoxide. We open up to the primary alcohol here, which is different than what we taught you before. So that kind of gives you an idea that this primary chloride must go first, okay? Which is true. It's a little easier to do SN2 chemistry on a better leaving group like this, even with the ring strain there. But you're given the product here, and the issue here is just to slam it home to the product following a reasonable mechanistic pathway. You don't need to worry about all the aspects of a new type of reaction like this, okay? So that's the challenge there. So what do we get to? We would get to this acetoacetate with our compound right there. And that would be just this bond here made, okay? And we have more. I should have mentioned two equivalents of sodium methoxide, I guess. The first one does that, and then, yeah, you need a second. Just like here, we had the two, right? And so let's see, we can form the enolate again, and then what? You have a choice here, either attacking here, and that will actually lead to the product. This pathway here, which we're not following, actually is the better pathway if you look at the epoxide, but a 5-membered ring here with the epoxide opening up exo to the 5-member ring actually is the favored pathway. That goes beyond the scope of our class. It's called Baldwin's rules. If you want to learn about that, take CHEM352, advanced OChem. But you just need to account for this product, and it's this pathway here, this arrow, you see. And if you open that up, what do you get to? You get to this here, which will have the 5-membered ring and the O minus. And then I think you can see from there, when you acidify, you protonate to form the alcohol there, and then you hydrolyze the methyl ester. If you heat this up, you can decarboxylate, just gets the methyl ketone. If you heat it up with more acid, you actually get a migration here and a double bond here, because this is a primary alcohol, and you can dehydrate this to some other things. So it's kind of a complicated thing. It's kind of an intermediate in the prostaglandin synthesis. Remember, we talked about prostaglandins. They're 5-membered ring compounds with these nonpolar chains that come off. Anyway, there's a little review for you. Topics from what? Chapter 23. All right, let's get into the main event here, which is the Aldol reaction and the Claisen reaction, the Diekmann and the Robinson. And the Robinson will kind of be the ultimate here for us. Now, I like to show the commonality between the Aldol and the Claisen, okay? What we're going to have is the enolate of one equivalent of the aldehyde or ester, and it's going to condense with itself. So we're going to look at this dimerization, you can say, here of this. So here's our enolate, which is going to be the nucleophile, right? We've already formed it here, and it's the resonance structure with the double bond here and the O minus there. And that's actually the true character of an enolate. But it's nucleophilic at carbon. Why? To give back the CO carbon-oxygen double bond resonance. Let's go ahead and attack here. And what we get is the same thing for both the Aldol and the Claisen reaction. We get back the carbonyl right there, okay? Now, if H here equals hydrogen or alkyl carbon, that's not a good leaving group, right? We just talked about that. We just reviewed that. So if you quench here with water or whatever, you get the aldol product, okay? Where it's an aldehyde or a ketone, whatever, aldol, okay? But look, if this tetrahedral intermediate, and that's the same thing we've been talking about, right? Adding to carbonyls. If this is a leaving group, if X equals oxygen here, that's an alkoxy group. And that can come off. That's a weaker bond, this carbon-oxygen bond. So this mechanism here for the Claisen, different than the aldol, but very similar, right? If we have an ester here now, we get this, okay? There's some other type of thing there. So very different products, you can say. They're both substituted beta positions here. One, though, has a ketone at that beta position. The other is an alcohol. Okay, yeah, we will see some variations of the aldol where we can eliminate that and form the aldol condensation, the double bond right there. But I think this unifies the thing based on what you know before. That's tetrahedral intermediate. So you could say, well, the mechanisms are all the same. And I've warned you about that. Don't get lulled into false security here. Make sure you can identify based on the structure and the conditions how the variations occur within the different reactions we're going to talk about. Yeah, well, there's one other variation. Here's the Michael reaction, right? And that will give us a different thing too. And we'll talk about that more later. But that unifies the whole shebang, right? It's all carbonyl enolate stuff, either condensing with itself, aldehyde or ketone, or with the ester, or with alpha beta unsaturated carbonyl, the conjugate addition. And that, yeah, if you can keep that straight, that's going to really help you out. Okay, let's get into the aldol reaction. Let's take acetaldehyde here. Well, let me generalize it here at first. Let's say, we've got whatever aldehyde, okay? And if we react that with potassium hydroxide in water, sometimes we add some THF to get it more solubilized there. Let's see, what do we get product-wise? We get the aldol product. Okay. There's our aldol. Contraction of alcohol aldehyde, aldol product. And you can see, well, it's the same thing. We got the potential to form an enolate, but there's no alkyl halide in there, right? So the electrophile is itself, and the nucleophile is itself there. So, what's going on here? Let's give some specific examples with maybe some yields. So you see how this reaction is. Acetaldehyde, sodium hydroxide, 5 degrees. And that's the thing, we need to specify the temperature and be clear about that. The book sometimes doesn't specify it. You're not sure if you get the aldol product or the aldol condensation. But at low temperature, let me show you here the result with acetaldehyde. It's this product, 55% yield. Now that's kind of modest, but it's useful, right? We go from a 2-carbon aldehyde to now a 4-carbon aldehyde with another functional group in it, the alcohol. So yes, it is a very important thing. If we take the same conditions here, same starting material, and heat this up 80 degrees now, we can get the aldol condensation product. Okay. So if the temperature's higher, you see, sodium hydroxide, look, we get the butanal, okay, with the double bond right here. So same 4-carbon species, but different functional groups result here based on the temperature. And so the mechanism will have to account for that, and we'll see what goes on. Let's see another specific example here. Let's take butanal and react that with potassium hydroxide at 100 degrees. And what do we get? We get the aldol condensation product. It looks kind of funny, and I like to show these more complex examples right up front. You can see 1, 2, 3, 4 carbons. There's 1, 2, 3, 4. This part came from the electrophilic part. So we'll be looking at the mechanism in a second here. And this part here, you see, is where the enolate was. That's the nucleophilic part. And if you let this reaction go carefully and isolate that product, 76% yield. That's pretty good. Okay. So yeah, these are useful things. And you can form some complex products from simple aldehydes here that have that. So let's do the mechanism now. So what do we need to see? We need to form first the enolate. Okay, so sodium hydroxide. And how are we forming that enolate? Well, we're grabbing the proton and forming the enolate. Okay. Now, you should be okay with that, but there's a couple things to say. What's our byproduct here? Water. And we're in water anyway, okay? So that's not a big deal. But what about the equilibrium here? This is highly reversible. Why? pKa of water is 15, right? What's the pKa of this hydrogen alpha to an aldehyde? Well, it's about 19. It's around 20, whatever. So the K for this reaction, this step here, is 10 to the what? Minus 4? That means it's only a part per thousand that's actually forming in the equilibrium here. So how can this reaction even work at all? Well, we need to look at the overall process. There's no other electrophile in here. And yeah, it is just reversing back. But if it collides with itself, the neutral form, the electrophilic form, what occurs here? So here we have a nucleophile, right? Let's go ahead and condense, or dimerize, if you will, the nucleophilic part of the aldehyde, which is formed in small percentage, less than 1% is actually this enolate. But if it sees this neutral form, which is what most of it is, you can form a new carbon-carbon bond. And what's that going to do for you? That's going to be very downhill, okay? Very exothermic. Why? Because carbon-carbon bonds over 90 kcals per mole, okay? And so what do we get? We get O minus tetrahedral intermediate. Push the electrons up, right? Reform the aldehyde here. So here is our nucleophilic side. There was our electrophilic side, okay? And let's say we're at 5 degrees, cold temperature. What do we do next? Well, we've got some water. Let's go ahead and protonate that. And what do we get? We get the aldol product, right? And so it looks like this. Okay. And if we're careful and adjust the time, we can monitor for the appearance of that product there. But yeah, we can get that in reasonable yield, and at low temperature, that's it. That's your aldol product. Okay, but if we're at higher temperature, if we're adding heat, 80 degrees or 100 degrees, oh, and that kind of gives you a clue here. 100 degrees, what are we going to start to do? Well, we're going to start to eliminate water, pull water out. And we don't have to have pure water here. We can have water THF, okay? And so heating it up, we've got to condense it back down. And then what are we going to do here? Let's see. Well, we can reform more enolate. We've still got hydroxide. So what are we going to do? Form some more enolate. And once we have that enolate of the aldol intermediate, it'll look like this. Okay. And what? Can bring this down and remove what? Oh, we're removing hydroxide. Now that should set off some alarms for some of you. What did we say in CHEM352? How good of a leaving group is hydroxide? It's not a leaving group. It's a horrible leaving group. We never do displacements SN2-wise with hydroxide. Alcohols are not good electrophiles for SN2 reactions. How can we use hydroxide as a leaving group here? Well, a couple things. We are in water and strong base. So creating some more base is okay. This carbon-oxygen bond is next door to an enolate. And that's the only reason why this alcohol can eliminate at that point. You can't eliminate alcohols on their own. Oops. Okay, sorry. Is it still working there? Sure, still coming up. Okay, sorry about that. Yeah, my AirPod just took off there for a second. Sorry about that. Maybe it was upset about this hydroxyl being a leaving group, probably. Okay. Yeah, my AirPod didn't like that. All right. But yeah, why can we do this? Well, we're in strong base. So reforming some strong base is okay. Before, when we had alcohols as leaving groups, we converted them first to hydronium ions and did dehydrations, but that was under strong acid conditions. Now we're in base with an enolate right next door here, okay? So you can't just eliminate any alcohol. It's this enolate right here. In fact, we're going to call this mechanism E1CB. And what do you think the CB stands for? Well, it's the conjugate base of our aldol product. Okay, which at higher temperature we can reform, and then it's a unimolecular reaction. The loss of hydroxide is within the same molecule. Base isn't coming in and pulling it off. Don't do the elimination like this directly. Okay, that would be a bimolecular reaction. This elimination reaction to form the aldol condensation product is known to be unimolecular. It just depends on the concentration of this new enolate. So it's unimolecular, it's elimination, and it's the conjugate base. Okay, so it's not E2. If you draw this as E2 or pick that on a multiple choice test, we'll mark it wrong. Okay, it's unimolecular through the conjugate base. And this only forms at high temperature, but we can get that in high yield, again, if we change the temperature. And you can just start it out at that high temperature and do the whole thing. The intermediate will be the aldol product. And if we're at low temperature, could isolate that in reasonable yield, but it'll just go on to the final product there. Okay, good. I think that's enough on the mechanism, the reversibility there. It can go under acidic conditions, and let's show you a little bit on that and why it might work. It's not as efficient though. You can imagine it's going to be a different set of conditions here. So HCl water will give some aldol product. It's much lower yielding and it's very slow. And why is that? Well, water HCl will allow us to form the enol, okay? And under acidic conditions, that's it there. So the enol then can function as the nucleophile. And if that occurs, we can add that in. We can increase the electrophilicity, though, of the electrophilic part. And that would give us this intermediate. And then we'd have to lose the proton off this here. And we can easily do that with water, okay? So this mechanism's fine. Why is this not as good as the base-mediated conditions for the aldol? Yeah, the enol here is neutral. It's not charged. It's not as good of a nucleophile there. And there's some other things that can go on under acidic conditions that are not productive there. So I like to show the mechanism, and it can go, but it's not the same thing. Okay, intramolecular versions here. Yep. So the aldol's very versatile. That's why we're talking about it. The aldol is seen in biology too. We'll see in metabolism later on that we can identify the aldol reaction in the glycolysis pathway, the conversion of glucose into pyruvate as actually a reverse aldol step. Gluconeogenesis, making glucose de novo in a cell, goes through the forward aldol reaction. We'll talk about that later. But let's see, if we take this diketone here, and ketones can undergo the aldol as well. They can form enolates, of course. Let me give you the product in this case. And let's see, we heat this up. You can get this 73% yield. And how does this work? Well, here we see our our new bond here, aldol condensation, and we are heating this up, let's say 100 degrees, just to make sure we're clear there. So yeah, we're going to do the E1CB elimination there of our product. And yeah, so this part over here, you could say is going to be the nucleophile. Here's where our electrophile is going to be. I've got it set up here to do that. So let's form the enolate right here. So I'm kind of jumping ahead on the mechanism. Now we could have formed the enolate over here. In fact, there's more over there. Or the enolate here or here. Well, it's a symmetric molecule. So really, here's our two choices. Why are we forming it here? Well, that follows then a six-membered pathway, and that's what the product is showing there. But why wouldn't it form over here? That's the more substituted enolate. But if we have it here, look, intramolecularly, that would be a four-membered ring then. Whereas the enolate up here gives us a six-membered ring. We'll have other opportunities look at intramolecular aldols and Claisens where we've got to make that decision. But if we follow this pathway here, what do we get to? We get to the aldol late, sometimes that's called, C intermediate, and we need to protonate then with water. And what do we get? We get the aldol product. So again, that's the aldol, but we're not stopping there. Why? Because we're at 100 degrees, okay? So, and we've got what? The ability to form more enolate right here. So yeah, let's do that. More hydroxide, more enolate, and that will give us this enolate, O minus, and hydroxide. So what do we do now? Can we get to the product? Yeah. So bring the electrons back down, and what? There's your friend hydroxide as the leaving group, and I'll check my AirPod to make sure it stays in this time. Oh, it did. Okay, so it's okay now. We explained why it's here, but yeah, giving us the intramolecular aldol condensation product from a ketone. Okay, so a little bit different there. Let me give you another example of this. And we've got this dialdehyde. So we've got some choices here to make. Let's look at KOH and heat. And what are we going to go to? Well, we're going to go to this product. And let's see if we can help you figure this out. It's right there. 89% yield, pretty good. And we've got, what, 6 carbons here. Here we're forming a 5-membered ring. So what are we going to do here? Well, we can form this enolate and then condense right there. And then I think you can figure out the rest of the mechanism there. There's our 5-membered ring. This is the nucleophilic part. This is the electrophilic part. And yeah, we're at higher temperature, 100 degrees. And yeah, we'll form the aldol condensation product right there. All right, do you always have to have the same aldehyde or ketone? No. You can mix it up. So let's say we've got this aldehyde, propanal, and acetaldehyde. And let's just do the aldol reaction. So here's sodium hydroxide, 5 degrees. What are the products? How many products are there going to be? So we call this what, a crossed or a mixed aldol reaction? Why do we say crossed? Well, we've got 2 different aldehydes. Well, what are the requirements here for the different functions in the reaction? Well, it's got a carbonyl, so that can be the electrophilic part. Both of them can be the electrophile. You can form the enolate here or here, so both can be the nucleophile. What are the products? How many of them are there? And let's put a challenge here. How many constitutional isomers are there? And how many possible stereoisomers are there? Now, if we were in person, we'd have a little class activity and try to figure that out. Use the mechanism to help you figure it out. Pause your video here. How many total isomers and how many total stereoisomers are there? Okay, we're back. So we'd have this aldol product, which would be what? The acetaldehyde condensing with itself. That's what we saw before. We'd also have the propanol condensing with itself, right? So we'd have this with itself. Now, don't forget about this methyl group right here. There's our nucleophile of propanol, right, condensing with itself. So that's 6 total carbons there, and you have a methyl group right there. These are the self-condensation products. How many crossed ones are there? That's what we're really trying to get out of here. Well, let's look at it just as I've drawn it here. We'd have this one. Okay. That one turns out to be the major one, actually. 37%. But there's a lot of other compounds in here. Now, this is a cross one. Here's propanol with acetaldehyde, right? So let's do acetaldehyde as the electrophile and propanol, you see, as the nucleophile, okay? So here you see propanol. The enolate must have been here, and here is our electrophile part there. So those are the 4 possible constitutional isomers, right? Which is the order of the bonding. How many stereoisomers are there, though? And there we're talking about stereocenters, right? And they can come in 2 flavors, R and S, right? So let's see, are there stereocenters created in the aldol? Oh yeah, there's one right there. So plus minus, the R and the S, solid wedge, dash wedge, so there's 2. How about here? How many isomers? Oh, there's stereocenter. Oh, there's a stereocenter there. So that's 2 to the 2 power. So that's what? 4 possible ones. Draw them all out if you want. Have both of them coming out, okay? The hydroxyl and the methyl, or both of them going back. This would be a pair of enantiomers. Have one coming out and one back, and then the other going back and this one coming forward. There's diastereomers within that 4 here, right? There's pairs of enantiomers and then many diastereomeric relationships. So that's 4 for that guy. How about this one? That's a stereocenter. That's a stereocenter. So there's 4 more there. Okay. How about this one? We just have the 1 stereocenter, so that's plus minus. So how many total stereoisomers are there going to be? Yep, 8, 9, 10, 11, 12. Wow. Okay. So, yeah, this is a bad mixture. Why is this one the dominant one? Let's see. Well, wait a minute. Okay, I think I've got that wrong. This is the 37% one here. And that's because the propanol one is the more substituted enolate. And the more substituted enolate is usually the favored one, but again, it's equilibrium here. You're forming a lot of that enolate too. But this enolate here, and it's only slightly more favored. These others are, 20 or so percent each one too. And then this is the smallest electrophile. And the smaller the electrophile is, it's just a methyl group here instead of an ethyl. So this combination is actually the better one for the major one. And I don't expect you to know that or analyze that. We're just pointing this out right now. With these simple aldehydes here, the crossed process is very complicated and gives a bad mixture. So how do we overcome this? Well, there's a couple ways to deal with it. You can do a crossed aldol reaction, low temperature, whatever, with one that only has the potential to be the electrophile, okay? So here we have the simplest aldehyde, right? Formaldehyde. And we have acetaldehyde. Sodium hydroxide, 5 degrees here. What's the product? Oh, I've got the results with propanol. Propanol, you see, can be the nucleophile here, or it can be the electrophile, right? But this is a more hindered electrophile. This is a smaller, simpler one. So you can actually get a good yield of this crossed aldol, where this is your only electrophile, okay? And the product here is isolated in good yield, 63% for that. Okay? Yeah, you get some of this self-condensation here, but by far the major one is this one, for the reasons we pointed out there. Crossed aldol, where only one can be electrophilic there. Let's see, so other ways to do crossed aldols with selectivity, yeah. We can take this one, benzaldehyde. Now, can that be the electrophile or the nucleophile? Well, again, it's only has the potential to be the electrophile. Why? You can't form the enolate here. There's no alpha hydrogens to pull off and form the enolate, okay? Let's condense that with acetone. And we're gonna do sodium hydroxide and heat, 80 degrees. So what are we gonna get here? Here's our nucleophile, and there's our electrophile, and our aldol product, if we stopped it there at lower temperature, would be that. But if we're at higher temperature, what does this go to? Right, we go to the alpha beta unsaturated ketone product there. And that can be obtained in high yield, 83% yield there for that. Now you could say, well, why doesn't this just condense with itself? Well, this is a ketone, so the electrophile here, it's a little bit harder to attack because this electrophile, you see, is an aldehyde with a smaller hydrogen there. So the self-condensation of ketones is a lot less efficient than the self-condensation with aldehydes due to the sterics. The approach to the electrophile part of a ketone is not as good. But these mixed aldols or crossed aldols with one that's a lot smaller or has no alpha hydrogen, it has to only function as the electrophile, and you can get that type of product. All right, here's another one. Maybe we'll look at this one in the reverse direction. So how would you make this? And maybe you remember the name of this compound. What is that? Yeah, that's cinnamaldehyde. Now you can get cinnamaldehyde from the cinnamon tree bark and isolate it and grind it up, whatever, and that's what you can buy at the store. Or you can make cinnamaldehyde synthetically, and that's how most of the ingredients for candy and a lot of other food products are. It's the same exact stuff from the cinnamon tree. It's just made synthetically and a lot more cheap. And so how do we do it? Well, here's an aldol condensation opportunity, right? And what's it going to be? Well, it's going to be that same aldehyde, benzaldehyde, and it's going to be acetaldehyde this time, and KOH, and heat, okay? And yeah, the yield's good there. You make that product. A couple things to say here. How come you don't get the self-condensation product here? Well, you do, and you know, some of that is going on. It's a byproduct there. But look, this is your electrophile here. And once you add there and then condense, eliminate water, you get the fully conjugated product here. So due to enhanced conjugation, and you can recrystallize this and get this away from the other products there. But yeah, another thing to mention here is how come we don't just keep adding more enolates here and polymerizes? How come we don't go on and make more of this? Because this would be even more fully conjugated, right? So we could do another aldol here, right? Well, once you have this conjugated here, this is not as good as electrophile, okay? Once it's fully conjugated here, you're pushing some electrons out here. That's then limiting the ability of a nucleophile to come in there relative to the initial one. So this is a better electrophile than the unsaturated aldehyde electrophile. So you can get a good yield of cinnamaldehyde from this. But you can imagine some other byproducts, and I'll just mention that. Having this in conjugation here gives you that resonance effect that is beneficial to the reaction. So it will eliminate right there and give you that type of product. All right, let's look at a couple other crossed type aldol reactions. See what else we've got. You can do malonate or acetoacetate type reactions here with aldehydes. And the base you're going to use now is the methoxy, sodium methoxide. So it's a little different than hydroxide. And let's add in that same aldehyde. So benzaldehyde here. And I'll let you go through the mechanism. You can see how this is going to work. You have to heat this up. But you can get this type of product, okay? So that's an aldol reaction with an ester enolate with an electrophile carbonyl that doesn't have any alpha hydrogens to become the nucleophile, so it can only be the electrophile, and then loss of water at that point with the excess base can give you that opportunity here. Now, let's use LDA to do what's called a controlled aldol. And what do we mean by that? Well, LDA allows you to irreversibly form the enolate wherever you want, on whatever carbonyl, and make that specifically your nucleophile, okay? In fact, let's combine this with the regioselectivity issue. Let's take this ketone here with LDA, and you can actually do this at low temperature, and then carefully add in, okay, in a second operation, your aldehyde. And you still keep it cold here, and then you add in your water. Okay, what's the product going to be? Well, you're not going to have these out of control crossed aldol products. This is going to be your nucleophile, okay? And this is going to be your electrophile. Why? Because we're preforming the enolate right here. And we can form the enolate over here or here. Do you remember which side we do it from? Yeah, the less hindered side. We're going to form the kinetic enolate. So it's going to look like this. And at that position, you know, the bulky base can only get on this side, not this side. That's the thermodynamic enolate. We could have preformed that too. We could have done the aldol controlled over here with what? Sodium hydride or sodium amide. We're using LDA right here. And then the aldehyde comes in. And, you know, this enolate is there. That's our nucleophile. It's already preformed, and it's at low temperature. We're not equilibrating anything there. There's no water in there yet, okay? This is usually done in THF or ether, okay? So it's no proton source, so it's not reversible at all. Irreversible, and once this is dripped in, it just reacts right there, okay? And then after quenching with water, what are we going to get? What's the product here? Well, we're going to get the aldol product on this side, get back the ketone there, and back the ethyl there. So you see the control you can get doing the aldol specifically using these irreversible bases opens things up. So yeah, you can limit crossed aldols either using something that can't be the enolate, can't be the nucleophile, it has to be the enolate. Okay, let's see, that might be a good place to stop for the first hour. I think we're okay on the time there. And that's the aldol reaction. So we did the self-condensation with simple aldehydes. We did the crossed aldols. And there you need to examine the structure. Which one can be the nucleophile? Which one can only be the electrophile is the key thing. And then the intramolecular version. So we did a lot this first hour, didn't we? Even though it's just the one reaction, okay? You've got to examine the structure. And that's why I say, you know, organic chemistry really has that hierarchy. Structure is everything. That's what leads to the reactivity. And then what's the reaction, you know, knowing what combination of starting materials go to what product. And then, of course, the mechanism and using the mechanism to unify the concepts together. This is a very good example where it should all come together, hopefully. But let's take a pause for the cause here. 10 minutes, and we'll be back with the second hour today.